So just have another look at this sketch here. Okay. We explained most of it. These are geostrophic horizontal flows, persistent Indian Ocean. We do a little bit towards the end of this lecture. Talked about western boundary currents, eastern boundary currents. But however, there's one feature we didn't discuss, and this is the equatorial countercurrent. It's this one here. Okay. What creates these countercurrents? It's called countercurrent because it actually runs against the direction of the north equatorial current and the south equatorial current. Okay, which are the limbs of the subtropical gyres, and actually it also runs opposite to the wind direction. How does this work? Okay, let's have a look at that in more detail. And this is now shown in this little sequence shown on the left side. So just doing it step by step. Okay, the starting point is look at the wind distribution. The distribution of wind speed is shown here on the left. Let's see with the mouse. The mouse is here. This is a top view. You look from above. Okay? You look from above, and you have look at an area which starts at the equator. Okay, and then you're 20 degrees north, 40 degrees north, 60 degrees north, 80 degrees north. And you look at the wind distribution. And the winds are essentially zonal winds. They're from east to west or from west to east. And you can see the trade winds. Okay, look at the trade winds. You also see a feature which is known as the doldrums, which is just north of the equator, just a zone of where the winds are generally weaker. Okay, if you go further to the north, you see the zone of the westerlies. Okay, and then further north of 70, or peaking at 70, the easterlies, polar easterlies. Okay, so now the next step is you have to think about Ekman layers again. You hope that you can ignore these, but Ekman layers, they are there. And that's the golden rule. They're deflected to the right with respect to the wind direction in the northern hemisphere, plus the volume transport actually also depends on the wind stress. So the stronger the winds, the larger is the Ekman transport. So now, based on this first panel of the wind speed distribution, you can now draw Ekman transports, and you can make the errors longer and bigger in zones which have the swiftest, the strongest winds. And then you can produce this panel here of Ekman transports. Okay, and you can see that there are some zones which have strong winds and some which are weaker. So now you can place little control volumes, we call them, over certain different regions here, and you can think of whether these Ekman transports create a convergence or a divergence horizontally. So whether they're actually the sea level is lifted up in a zone where you have a convergence, or is lowered, is pushed downward in a zone of divergence. And you write convergence if you are in the zone of convergence, or divergence if there's a zone of divergence. You can see convergence here. You can play around with that. And if you have a convergence, you write H, okay, because it produces a high pressure. Or an L, because it produces a low pressure. Okay, and then you think in terms of what are the geostrophic flows created. Okay, and they are not from high to low. No, they're not from low to high. Oh no, even a double no. They're instead, you create zonal currents initially in the ocean, in the open ocean, either from west to east or from east to west. And if you look close to the equator, you actually produce a current which is the north equatorial countercurrent, which runs opposite to the wind. The winds are weak there, but it opposites to the wind, which is the north equatorial countercurrent. And next behind me, you can look at it. It's actually more a map of how it looks like if you look from above. You know, you have the western boundary current on the left, and you get the north equatorial countercurrent, yeah, which is just near the equator. So why do you get it? Why is it only north of the equator in this situation? And the reason is because the doldrums are a little bit shifted, a little bit northward shifted in that. They don't sit exactly over the equator. So why is this? Why are the doldrums not located exactly over the equator? Well, it has to do with the distribution of land masses and continents in the ocean. Okay, that is the explanation of this feature. Okay, pretty long this slide, but I think it's nice. So what I did is actually something that you should do. You look at the sketch, go through it one by one. You would apply all your knowledge about Ekman transports, knowledge about geostrophic flows. Okay, and then you can explain these type of persistent patterns of currents that you have in the oceans. It's very important because your grandma just wants to go onto a trip with her rubber ducky. She wants to cross the Atlantic Ocean, with her paddle boat. And well, it's good to know that how the currents are in that area. So otherwise you easily get lost.